Hello everyone. So in this lecture I will continue our discussion on basic concepts of atom. Here I will talk about a hydrogen atom ground state, many electron system, many electron atom like helium, lithium having more than one electron, how to represent the electronic configuration of different atom and their related properties. So first I'll talk about the ground state of hydrogen atom. So far we have focused on the atomic orbital of hydrogen. I have shown you different atomic orbitals, their shape, their origin, and have talked about the probability of finding an electron in different atomic orbital. The most energetically favorable state of hydrogen atom is in its ground state. That is the most stable state, lowest energy, in which a single electron occupies the 1s orbital. This electron which resides in the 1s orbital can be promoted to higher energy orbital also to give an excited state. So the notation from the ground state of electronic configuration of hydrogen atom is represented in this form. 1 is 1. Where S is the orbital which contains this one electron and 1 is represents the principal quantum number. This signifies that the one electron occupies in the 1s orbital. Now we move towards the many electron atom, how to deal with that kind of system, how to represent their electronic configuration. Hydrogen like species containing one electron, the energy of those kind of species depend on principal quantum number n and as well as the atomic charge, that is the atomic number z. The atomic spectra of such kind of species contains only a few lines associated with changes in the value of principal quantum number. It is only for such kind of system, one electron system, those cases Schrodinger equation has been solved exactly. The next simple atom is helium, having more than one electron. Z is equal to 2. Atomic number is equal to 2. For its two electron, three electrostatic interaction must be considered. So there is three interaction will be considered in order to solve that Schrodinger equation. First is the attraction between the electron 1 and the nucleus. Second is the attraction between the electron 2 and the nucleus, and third is the repulsion between this electron 1 and electron 2. So the net interaction determines the energy of the system. In the ground state of the helium, the electronic configuration is 1s2. That is, two electron resides in the 1s orbital, and the spin value of these two spin quantum number of these two electron will be ms is equal to plus half and minus half. For all atom except hydrogen like system, orbitals of the same principal quantum number but different values of L are not degenerate. So in case one of the electron of helium is promoted to the higher energy level orbital, for example let's say n is equal to 2, then the energy of the system depends upon whether electrons goes either 2s orbital or 2p orbital, because in such kind of situation give rise different electrostatic interaction. However, in case of 2p orbital, if the electron goes, there will be no distinction among the different 2p orbital. Similarly, case also d orbital. If the electron is promoted to any of the d orbital, there will be no change in the energy. It will be similar, same. But for n is equal to 3, so there is three possibility: 3s, 3p, 3d. So in terms of obtaining wave function and energies for the atomic orbital of helium, so in terms of obtaining the wave function for helium, it has not possibility to solve the Schrodinger equation exactly. Like one electron system, hydrogen and hydrogen like system, for example helium plus, it is possible to solve the Schrodinger wave equation exactly, and thus we can get the everything of that particular atom. But when in case of helium or more than one electron species, it has not been possible to solve this equation, Schrodinger equation exactly, and only approximate solution are available. For atoms containing more than two electrons, it is even more difficult to obtain accurate solution to the wave function. Now coming to the electronic configuration, how to represent, how to write it, and what are the main important things to look at. So far we have already seen that electronic state of hydrogen and helium, that is 1s on 1s2 respectively. Now the 1s orbital, when it is fully occupied in helium, its configuration is often written as helium within third bracket. In the next two element, lithium, which has atomic number 3, beryllium 4, the electron goes into the 2s orbital. And then from boron to neon, 2p orbitals are occupied to give the electronic configuration helium 2s2 2pm, where m can vary 1 to 6. When m is equal to 6, the energy level or cell with n is equal to is fully occupied, and the configuration of the neon can be written as neon within third bracket. Similarly, the filling of this 3s3 orbital takes place with two electron in the 3s and 6 electron in 3p. An analogous sequence comes from sodium to argon. The last element in this series having the electronic configuration, fulfilled electronic configuration uh, with argon, that is having 18 electron. With the electronic configuration can be written as neon within third bracket 3s2 3p6. Neon has 10 electron and 3s2 3p6, 10 plus 8, so 18 electron argon. So this kind of noble gas configuration we have to retain. Then we can add the electron in the orbital to represent the electronic configuration of atom having such kind of electrons. So here I have given the sequence, the following sequence in order to fill the atomic orbital is approximate to relative energy, lowest energy first of the orbital in the neutral atom. So you can see that first you put the electron in 1s, then 2s. When 1s is filled, the electron goes to 2s, then 2p. When 2p is filled, electron goes to 3s, 3p. Then you will not go to 3d. First it will comes to 4s, then 3d, 4p, 5s in this sequence only. So if you see that figure, so electron will go in this way. So this is the principal quantum number n, and this is the azimuthal quantum number l. Is equal to 0 means s orbital, 1 means p orbital, 2 means d orbital, 3 means f orbital. So electron will fill in this sequence 1s, 2s, 2p, 3s, 3p, 4s, 3d in this sequence. So one of the electronic configuration I have written over here, calcium has 40 electron. Calcium has 20 electrons. So how to represent calcium? So you can write in the normal way, like just filling 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So overall you will have, you can see that 2, 2, 2, 4, plus 6, 10, 12, 18, 20. So either you can write in this way also. You can take 18 electron like 1s2, 2s2, 2p6, 3s2, 3p6. You can represent by argon, because argon electronic configuration is like this. One is this argon electronic configuration. This is the electronic configuration of argon. So you can put argon and then you can write 4s2. So this is a noble gas configuration argon. You can represent it within third bracket parent place, and then you can put 2s. So it is the electronic configuration of calcium. So this is 18 plus 2, 20. So this is how one can write electronic configuration of any atom, provided you have to know the atomic number. Then you can write the electronic configuration. Now comes to an important topic, penetration and shielding. In order to understand better the electronic configuration and the details of the atom, you have to understand this topic, penetration and shielding. So penetration describes the proximity of the electron in an orbital towards the nucleus. So when the electron resides in orbital, how much it is in proximity to the nucleus. If the electrons which experience greater penetration experience less shielding and therefore experience a large effective nuclear charge. But those kind of electrons which are much more penetrate towards the nucleus, they shield other electrons more effectively. So in general, penetration effect is that due to the shape of the orbital, for example, s orbital, it penetrates more nearer to the nucleus than the p, d, f orbital, and it is more tightly held. Now, what is shielding effect? This inner electron, this for example, this s electron or p electron, this inner electron between the valence electron and the nucleus. So there is a nucleus. You can see this picture. This is the nucleus in shown in the yellow color. This is the nucleus and the valence electron, the outermost electron, valence electron. So for example, this is the electron of interest. This black color. This is the electron of interest. This is the nucleus, and in between this is the electron in between, which is the inner electron, which actually shields this outermost electron to experience the fully nuclear charge fully. So the inner electron between the valence electron and the nucleus shields the valence electron from the nucleus, is called shielding effect. So basically, you can understand from this diagram, tutorial diagram, you can see that this is our valence electron. This is electron of interest. This is our nucleus, positively charged nucleus. So this electron in between cancels some of the nuclear charge. Basically, the electron which in this green region, which shields the outermost electron. Therefore, this outermost electron, valence electron, cannot fully experience the nuclear charge. For example, if this nuclear charge is, for example, 10 unit, then this outermost electron will experience, let's say, 5 unit or 6 unit. The remaining 3 4 unit they will not experience, because this is shielded by this inner electron. The inner electron shielded this effective nuclear charge. Therefore, the outermost electron cannot experience it fully. However, this inner electron, because of its penetrating power and the shielding effect, they are having large effective nuclear charge than this outermost electron, this electron of interest. So this is the trend within the same cell, like same value of principal quantum number n. The penetrating power of an electron follows this trend, like s, p, d, f. So s orbital is much more penetrating than p, which is higher than d and f. So the penetrating, so this is the important part, penetrating power much more higher for s, greater than p, greater than d, greater than f. So which means that s orbital shielding power is also much more than p, d and f orbital. And for different value of nl in case, then penetrating power of the electron follow these trends. This 1s, 2s, 2p, 3s, 3p, 4s, 3d. So if you look at this sequence of this penetrating power sequence with different values of nl, you will understand this sequence is exactly similar than that of sequence I have shown in the last slide, where we can how we can feel the electron in the orbital. Now this sequence is actually coming because of this energy level, because of the this 1s, 2s, 2p orbital having lowest energy. With gradually moving to the right hand side, the energy will increase. So electron will first come to the lowest energy level, then it will automatically come to the higher energy level. So this is the sequence actually. So when this 1s, 2s, 2p orbital penetrating power is more, this means that these are tightly held to the nucleus. These are when electron fields occupies in this orbital, they are much more stabilized than the higher energy orbital. The electron probability density for s orbital is highest in the center of the orbital or at the nucleus. So if you actually recall the probability distribution graph, that kind of graph I have already talked about in the last slide, probability distribution curve, radial distribution curve, that kind of plot, that s orbital at the nucleus, it has a probability density at the nucleus. So it means that, yeah, there is a significant amount of s orbital is there at the nucleus. In the, if you look at the this radial distribution probability curve, electron which experience greater penetrating power experience stronger attraction to the nucleus and less shielding, and therefore experience a higher effective nuclear charge, but shield other electron more effectively. So I'll come to the part in detail, that effective nuclear charge, how to calculate this effective nuclear charge. So in general, it can be said that the orbital which having greater penetrating power, like s orbital, which are very close to the nucleus, they are tightly held to the nucleus and they actually shield the valence electron to experience the nuclear charge fully. So if you look carefully this radial distribution curve function for this 1s, 2s and 2p orbital for the hydrogen atom, that is 1s1 system, one electron system, you will see that 2s orbital shown in this blue color penetrates much more deeper into the 1s orbital. This is a 1s orbital plot, 1s orbital. So under the 1s orbital area, you can see that 2s orbital, there is a probability of the 2s orbital is there. So 2s orbital penetrates much more deeply into the 1s orbital than that of 2p orbital, which means that 2s orbital penetrating power is higher than the 2p orbital. So the radial distribution function shows that this 2s orbital penetrates much more deep into the 1s orbital than the 2p, and because of this weaker penetration power of 2p orbital, electron in the 2p orbital experience less effective nuclear charge, or they are experience a repulsive force, that they are shielded from the uh, nucleus. Basically, this 2p orbital, you can see that this 2p orbital, this 1s 2s, they actually shielded this 2p orbital electron, and because of that they actually cannot fully experience the attractive force of the nucleus. The deeper penetration of the 2s orbital means electron in the 2s orbital experience a greater force and to the nucleus and are not shielded as effective. So if you see this kind of radial distribution plot of the other orbital, you will understand the penetrating power sequence of the different kind of orbitals. From this sequence, you will understand 1s orbital is much closer to the nucleus. This is r is equal to 0 means the nucleus. At nucleus, 1s orbital probability is significantly higher than 2s or 2p. Then comes 2s orbital. 2s orbital penetrates much deeper into the 1s orbital towards the nucleus. Then 2p orbital. So by looking at the radiative distribution function, this kind of graph, one can understand the penetrating power of different kind of orbital. And because of this higher penetrating power, this kind of orbital are much more attractive towards the nucleus, and the electron is preferable to go in that orbital fast. For example, if we have 3 electron, for example lithium, so or if you take 5 electron system, for example boron, so first electron 2 electron will go to 1s orbital, then 2 electron will go to 2s orbital, then 1 electron go to 2p orbital. And why is that? Because of this kind of penetrating power shielding and energy difference. The energy, lower energy state will first occupy the electron, then will come to the higher energy level. Here I have given the chart for ground state electronic configuration of the element up to z is equal to 82. So you can see that by your own how to represent feel the electronic configuration in the different orbital. You will understand that I have already talked about this part, hydrogen, helium, lithium, beryllium, boron part. So I have already talked about the calcium also. So you can take any example. So for example, magnesium has 12 atomic number 12, so it means 12 electron it has. So you can write the neon electronic configuration first. Neon basically 10 inert cell configuration. In that case, you have to write inert cell configuration, then you put the other electron in the 3s orbital. So in that way, you can write the electronic configuration. For example, chromium has 24 electron. So how we can write chromium? So you first write the argon, means 18 electron, then electron will go to 4s orbital, then it will go to 3d orbital, 3d 5 orbital. So there is some catch over here. For example, this you take this example chromium, or you take this example copper. So if you look carefully, after filling the argon, one electron goes to first 4s orbital, then the remaining 5 orbital goes to 3d orbital. But however, in case of vanadium, if you see that after filling the argon, the 2 electron goes to 4s orbital, then the remaining 3 electron goes to 3d orbital. But when you move from vanadium to chromium, you can see the discrepancy. The 4s orbital is not fully filled, however 3d orbital is fully filled. So this is another consequence, is that this kind of d orbital, p orbital, when it is half filled or full filled, they are having much more stable energy state than that of partially filled orbital. So in case of to maintain this kind of feeling, like here 3d 5 means half filled orbital, and this kind of orbital, because of the exchange energy I will talk about in the upcoming lecture, they are much more stabler than that of 3d4 configuration. So if you write this equation, electronic configuration 4s2 3d4, it is comparatively higher energy than that of this system. So basically, when this kind of situation occurs, 3d5, 3d10, always give preference to that kind of electronic configuration, putting one electron in the 4s orbital. So in case of copper also, you can see that from zinc the electronic configuration is argon 4s2 3d8. So 4s orbital is fully filled and 3d each partly filled 3d. But when you move to nickel to copper, you can see that the 4s orbital is 4s1 and 3d is 3d10. So in order to maintain the full field configuration, the 3d is filled with 10 electron and the 4s orbital is remained in 1 electron. So this kind of thing one has to keep in mind. So this kind of 3d orbital for e orbital, they can stabilize this half filled orbital and full filled orbital electronic configuration. So in order to maintain this kind of electronic system, one has to put 3d5 3d10 orbital, and then they can maintain the remaining electron in the 4s orbital and the higher energy orbital. So this is very important thing to understand. And this kind of thing I have already talked about. This helium is 1s2. This is one of the representatives helium. This is a neon helium 2s2. This is argon. So based on this helium, neon, argon, so one can rewrite the other electronic configuration. Similarly, for if you see the krypton also 38, so this kind of system also you can use to write the other atomic electronic configuration. Now coming to effective nuclear charge and Slater's rule, how to exactly calculate this effective nuclear charge for the outermost electron, valence electron. So effective nuclear charge refers to the charge filled by the outermost electron, that is valence electron, when multi-electronic atom after the number of shielding electron that surround the nucleus is taken into account. So you can clearly observe from this pictorial diagram figure. This figure you can see is that this is a multi-electronic system atom do not experience the full nuclear charge. So this is the outer electron. This is the 1s orbital. This is the 2s orbital. This is the nuclear charge. This is plus 3. This is a representative example. For you see that this is plus 3 is the charge, nuclear charge. The inner shell electron, 1s orbital electron, it having experiencing this jet effective is equal to 2.69. 2.69. You take the value to understand the value, and you can see the outermost electron, the valence electron, 2s orbital, it experiences the jet effective is equal to 1.28. So it is much lesser than that of 1s orbital. So this is because of this 1s orbital shield screening this 2s orbital electron to experience the fully this nuclear charge. So effectively this nuclear charge experienced by 2s electron is 1.28, which is lesser than the 1s electron. So effective nuclear charge is the charge that each electron experiences. Each electron experiences. That means 1s, 2s. So normally valence electron, because of the screening shielding of the inner core electron, it actually experiences less nuclear charge compared to that of inner shell electron. So how to calculate this effective nuclear charge I will talk about in the later slide, just next slide. So now you see this. This is a periodic trend of effective nuclear charge, and this effective nuclear charge has a indirect relation to the atomic radius also. So this is the periodic table. So along the period, if you go from move from left to right, so Z effective increases. But Z effective, when it increases, it actually also means that atomic radius decreases. When this atomic radius effective increases, it actually signifies the atomic radius actually gradually decreases from moving down to left to right in a row. Similarly, in a column-wise manner, the atomic radius increases when you move from hydrogen to lithium, sodium, potassium, rubidium down the group. And down the group, effective nuclear charge also decreases. In vice versa, in upward direction, you can see this figure. The Z effective increases in the upward direction, like moving from higher radius to smaller radius atom. Like from moving to cesium, rubidium to sodium, lithium, hydrogen, the effective nuclear charge increases. So basically, the effective nuclear charge has an indirect relation to the atomic radius. As Z effective increases, atomic radius decreases. So this is the basically correlation. The effective nuclear charge, when it increases, it means that the outermost electron, the electron are tightly held to the nucleus, and automatically the atomic radius actually decreases. This is the general trend. Slater's rule for estimating effective nuclear charge, Z effective. So effective nuclear charge experienced by electron in different orbital, atomic orbital, may be estimated using Slater's rule. These rules are based on experimental data for electron promotion and ionization energy. And this Z effective is determined from this equation: Z effective is equal to Z minus S. But Z is the nuclear charge, Z effective is the effective nuclear charge experienced by the electron in different orbital. S is the screening constant or shielding constant. Now the important part is that in this equation, one thing we have to calculate, this is S value. So how to calculate this screening constant, shielding constant? So first you have to write the electronic configuration as in this sequence. I have already talked about the energy order, all these things. So you have to write down the electronic configuration in this sequence energy order. Then after filling the electron, so you have to calculate the screening constant n. How you can calculate? Now electron in any group higher in this sequence, then the electron under consideration contribute nothing to S. So basically, for example, if you can take any orbital or any group, any, for example, you take this 4s 4p orbital, this group. So electron in the right hand side like 4d 4m, it will not contribute to this 4s 4p orbital in order to calculate the screening constant, shielding constant value. So the all the electrons which are left to these orbital, this group like 3d 3s 3p 1s 2s 2p, they will contribute. But the electron which are right, which are next to the this electron of consideration, that will not contribute the screening constant, nothing to S. So this is the basically thing. The electron in any group, let's say this group 4s 4p, this group higher in this sequence, then that electron at a contribute nothing to S. So basically, if the electron you are considering 4s 4p, then the other electron at the higher energy level like 4d 4a 4s 5s 5p, that have nothing to do with the screening constant value. Only the left electron, the electron which are these electrons, this 3p 3d 1s, that will core electron will contribute, not the outside other electron. Outside electron will contribute. Now we consider a particular case ns np. So you can take this 4s 4p orbital, let's say 4s 4p orbital, this group. So in this group, in this case, this kind of electronic, in this case the other than that of that electron of consideration, for example 4s to 4p6. So if you want to calculate that outermost electron effective nuclear charge, you have to calculate in this way. Other than that electron in this ns-np orbital group, all the electron like 5 electron will contribute 0.35 to the s value. Each of the electron which in the n minus 1 cells, means here n is 4, so n minus 1 means 3, like 3s 3p 3d shall contribute is equal to 0.85. Each of the electron in the n minus 2 level, so if it n is equal to 4, so 4 minus 2 means 2, and lower level like 2s 2p and 1s, it will contribute is equal to 1. So basically, the if the electron is in this kind of ns np orbital, this kind of group, then other than that electron, all the electron in that group will contribute 0.35. Remaining the electron which are in the n minus 1 cell will contribute 0.85 to the s value, and n minus 1 sublevel on the lower sublevel cells, they will contribute 1 to that of s. Now there is another consideration. If the electron is in electron of interest resides in the d orbital, nd or nf orbital, let's say 3d orbital. So each of the other electron in 3d orbital or f orbital, it will contribute 0.35. So if the electron is 3d5, for example, then the apart from one electron, the other electron like 4 into 0.35, it will contribute to the screening constant value. Now each of the other electron in down the group in a group lower than that of being considered, it will contribute is equal to 1. So if your electronic configuration is up to 3d orbital, then all the previous orbital like 3s 3p 1s 2s 2p, all they will contribute 1, all they will contribute 1. Only nd orbital they will contribute 0.35, and the remaining the orbital which are core electron, they will contribute 1 to the screening constant value if your electron of interest resides in the d or f orbital. So you will understand it better when I will give you two example. then one can understand the Slater rule, how to utilize it to calculate the effective nuclear charge. So this is an example of how to apply Slater's rule. The question says that confirm that the experimentally observed electronic configuration of potassium is like that: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So this is actually energy order. I have already told about this is the general sequence of energy order. So this is energetically more favorable, stable than that of configuration 1s2, 2s2, 2p6, 3h2, 3p6, 3d. So basically changes is that here the last electron goes in the 4s orbital, here the last electron goes in the 3d orbital. So this is the first one is the actually experimentally observed electronic configuration. So you have to prove that this is more stable than that of the other in the second one. So how do you can calculate using the Slater's rule? You can calculate the effective nuclear charge experienced by this 4s electron and effective nuclear charge experienced by this 3d electron. Then you see that in which case Z effective is higher. In that case where Z effective is higher, that means that that nucleus is much more attractive toward the nucleus. It gives a much more stable orientation or configuration. So now comes to the how to solve it. So potassium Z is equal to 19. You can calculate this Z is equal to 19. So applying Slater's rule for effective nuclear charge experienced by this 4s electron for the electronic configuration. So for 4s electron, if you want to calculate the effective nuclear charge, you don't have you you so you you have to think the other electron apart from that electron of your interest. Electron you want to calculate the effective nuclear charge. So this is the formula. Z effective is equal to Z minus 1. So Z is equal to 19 for potassium. Now the important part is the screening constant calculation. So you see that I've already given the value in the previous slide. So this 3 orbital, these 3s2, 3p6, they will contribute 0.85 to the screening constant value because they are in the n minus 1 level. So I've already talked about the n minus 1 level will contribute 0.85. So they will contribute 8 electron will contribute 0.85, and the remaining electron in minus 2 and the lower level 1 or 2 principal quantum level, these two series 1s 2s 2p, they will contribute 1 to the screening constant. So there is 10 electron, 1s to 2s to 2p 6, 10 electron, 10 into 1. So overall you will calculate the screening constant will come out to be 16.8. So if you subtract 19 minus 16.8, you will get 2.2. So for potassium with 4s on electronic configuration, the Z effective comes out to be 2.2. Now you calculate by your own how for 3D one electronic configuration the effective nuclear charge, and you can match with the answer. So this is the electronic configuration. This is the formula: Z effective is equal to Z minus 1. The nuclear charge Z is equal to 19. Now for the D electron, apart from the D electron, you calculate the other electron to their contribution in the screening S value. Now this all the other electron. So I have already talked about the in case of D electron. So all the electron left to that electron of interest will contribute fully 1 to that of screening constant. So basically the 18 electron will contribute 1. So you will get the screening constant value 18 is equal to 118, and if you calculate the Z effective, it will come out to be 1. So thus an electron in the 4s orbital rather than 3d orbital is under the influence of greater effective nuclear charge, and in the ground state of potassium is therefore 4s atomic orbital that is occupied. So basic understanding is that you see that Z effective here 2.2, here Z effective is 1. So when this electronic configuration is 4s 1, the Z effective is much more. When this electronic configuration is 3d 1, the Z effective is lower. So when the Z effective is higher means it will under a greater influence towards the nucleus, and it is having the lower energy, more stable configuration. So in that way you can correlate your answer, you can understand the logic. Now coming to the last example of the Slater's rule. So what is the Z effective experienced by the valence electron in the three isoelectronic species? Fluoride anion F minus, which is 10 electron, neutral neon 10 electron, sodium cation 10 electron. So these are isoelectronic three species. However, Z effective will be different because of the atomic number will differ of the fluorine to sodium, neon and sodium. So how to calculate the Z effective using Slater's rule? I will I will also discuss here. and you can see that which atom actually experiences greater nuclear charge using Slater's rule. By looking at this Na plus neon F minus, one can understand the logic which will be much more having effective nuclear charge. But let's do the example and then we can conclude our talk. So each species having 10 electron and number of core electron is 2. So basically, if you fill in the way 1s2, 2s2, 2p6, okay. So 2s2, 2p6, this is the valence electron, 8 valence electron. Total 10 electron, 8 valence electron, and core electron 2 means this 1s2 electron. But the effective nuclear charge varies because each has a different atomic number. The approximate Z effective can be found out using Slater's rule. For all of the species, we would calculate the same S value. Because now you see that S value will be similar because because this fluoride, sodium plus in neon, electronic configuration is same. They are isoelectron. So the screening constant or shielding constant will be the same for three ion or three species. However, Z effective will different because all these three species having different atomic number. So calculating the S will be similar. You want one shot you will calculate S for three species and then you subtract with the atomic charge. So this is 1s2. Actually, uh, this is 1s2, 2s2, and 2p6. So this is a 10 electron. Now we calculate the screening constant. So the for 2s2p this series, so the total 7 electron you have to calculate. Uh, you have to uh, apart from that electron of interest, you have to calculate other electron that will contribute. So basically, although there is 8 electrons, so apart from the electron of interest, the 7 electron contribute 0.35, the core electron contribute 0.85. This 2 into 0.85 to core electron, 7 the valence electron into 0.35, we will get the value 4.15. This is the fixed value for all the three species. Now for fluorine atom, Z effective, Z is equal to 9 minus sigma. You can represent by S also, screening constant. So you will get the value 4.85. The Z effective value for neon, Z is 10. So the screening constant will be the effective nuclear charge will be 5.85. For sodium, the Z is equal to atomic charge 11. So the effective nuclear charge is 6.85. So you can see that from fluoride F minus, from F minus to sodium plus, the effective nuclear charge, that is Z effective, is actually getting increased 4.85 to 0.585 to 6.85. So basically Z effective charge basically increasing. Z effective, if you can see that Z effective actually increasing. So sodium cation has the greatest effective nuclear charge. You can calculate using the Slater's formula. Now logically you can also think of that sodium, because of the positive charge, it has much more attraction towards the nucleus than that of anion, fluoride M minus, and compared to the neutral neon atom. So basically in all these atom species, the electron is same, electronic configuration is same because they are isoelectronic. You first fill the electronic configuration, then you just remove one electron of your interest and other electron will contribute to the screening constant value. For example, here 1s2, 2s2, 2p6 orbital electronic configuration, the 7 electron will contribute 0.35, the 2 electron will contribute 0.85 as per the formula suggests. Then you just subtract with the atomic charge. For fluorine 9, for neon 10, and sodium 11, you will get the effective nuclear charge 4.85 for fluoride, neon 5.85, and sodium 6.85. By looking at that effective nuclear charge value, you will see that sodium cation has the greatest effective nuclear charge. Thank you for your kind attention. In the next part, I will talk about the last part of this series, basic concept of atom, where I will talk about the exchange energy and some about the periodic table and above principle. Thank you.